Good afternoon to everyone. Still good morning to our West Coast attendees and welcome to the webinar. This is Ed Solapira, the CEO of Predictronics. I and my colleague Aaron Shelley are here to talk about deployable predictive solutions aimed for downtime reduction, quality improvement, and process optimization that we hope can be relevant and beneficial for semiconductor manufacturing. We are so glad that you can all join us today. For today's webinar, we will discuss and share our experiences, findings, and insights, more like a lessons learned in configuring and deploying predictive solutions for semiconductor manufacturing. We will go through several case studies related to predictive maintenance, virtual metrology, and chamber matching. We will also provide a brief demonstration towards the end of this webinar for the use case and then conclude with some guidance on how one can get started with this initiative. Before we begin, allow us to share a brief background about ourselves. Again, this is Ed Solapira, and I lead a wonderful team at Predictronics, and I am primarily responsible for business development and partnerships. I have been fortunate to have worked with various organizations and customers in the semiconductor area, from past projects with ISMI, as well as our recent customers in this space. Meanwhile, my colleague Aaron is a senior data scientist, and his expertise is on the data science and the software side. He has been working very closely with our semiconductor manufacturing customers to configure and fine-tune predictive models and eventually deploy our solutions. So let's begin with an overview of the predictive solutions for semiconductor manufacturing. Various industrial market segments can definitely derive value from predictive analytics if appropriately utilized and applied judiciously. Predictive solutions in semiconductor manufacturing can be tailored for a predictive maintenance use case, in which the goal may be to extend the maintenance time window and lessen unnecessary replacement of components and consumables. We have one specific case study that will highlight this use case a bit later in this webinar. Another area is to find early symptoms of failure and reduce unplanned downtime. In addition, solutions related to virtual metrology and chamber matching can be used to improve yield rates and reduce costly metrology measurements. Now let's dig deeper into the various use cases. Semiconductor manufacturing is a complex production process that consists of different stages of operation. It generally includes, but not limited to, crystal growth, wafer slicing, etching, polishing, and inspection. Several manufacturing steps highlighted in this slide with the P symbol here indicate where Predictronics have had previous work or projects with the most hands-on experience on developing predictive solutions for the etching process. Just to elaborate a little more, this table provides a summary of our past work. We have selected the 6 most notable past projects related to this space for etching equipment, wafer slicing, lithography, and also on the Czochralski process or crystal growth. The topics of these engagements include predictive maintenance, virtual metrology, and chamber matching, and we have worked with both machine OEMs as well as with the fabs or the end users as well. Now let's get into the first case study, which focuses on extending the component lifetime, and this was for an etching equipment application. For the motivation of this use case, replacing a component too early is always very costly. So it includes downtime associated with the replacement, the cost of labor and the part itself, and the risk of imperfect or unnecessary maintenance. The solution that we have developed combined different domain-specific features with data-driven models so that we can estimate and predict the component's health over time. This enabled the equipment owner to replace the component or consumable only when it is needed. This can provide a significant amount of value in terms of reducing downtime and labor cost. Now, for the overall process of configuring and deploying the predictive maintenance solution, we follow our typical 6-step approach to this problem. The appropriate data is fortunately being collected already from the etching equipment, and the data is stored to a database. We then went ahead to segment the data by process step and extract the various statistical features. Since the number of features can be quite large, we use machine learning and statistical methods for selecting the features. The health model utilizes the top ranking features and compares these patterns to a known reference or a baseline condition. This multivariate health index is then tracked over time, and then time series prediction methods are used to infer when the component should be replaced. Now, the other two use cases that will be discussed by my colleague later on will employ a similar looking 6-step approach with different algorithms and settings and specificities selected for each of these for each of the steps. Now, for some details regarding the implementation, for this opportunity, we were fortunate to have worked with a Fortune 500 global manufacturing organization. They are a fab or an end user, and the goal of the engagement was to optimize the usage of a consumable part. The solution that was developed was evaluated and validated with 18 assets, and the results show that the component's lifetime could be extended by 25% for many of the assets. About the data set, we analyzed data coming in from 18 chambers, and the data was collected over a span of 6 months. So we had sufficient data for both baseline training as well as for testing purposes. The data included trace or sensor signals and output-related measurements, such as maintenance records, which included both preventive maintenance and unplanned events, as well as quality or metrology measurements. The sensor data consisted of approximately 100 signals. So it was a data-rich environment. Now, from our team's experience, we had to extract statistical features for each signal for each process step. This has worked quite well for us for this type of semiconductor manufacturing application. We calculate various statistical features such as mean, standard deviation, slope, range, and other goodness of fit characteristics. This analysis step generates a large pool of potential features that we can consider and investigate. As it is not practical to use all the features, we considered 4 different feature selection techniques. And from this study, as well as our past experience, a partial least squares feature selection method was the most successful, and it performed the best at finding features with a significant or distinct trend. Now, other methods, such as the Fisher criterion, were more suitable for comparing healthy versus faulty. So that, let's say you're faced with a classification type of problem. And they were less insightful in selecting the features we needed for the predictive maintenance use case. Anyway, the insight that we would like to impart with this slide is that we believe that there's no magic feature selection technique that would work best for all the use cases. We implore that you choose the right method for a different or specific application. Just to cite an example feature that was chosen from the feature selection routine, consider this plot here. As one can observe, this particular feature illustrates a clear decreasing trend from new component installation all the way down to replacement. So this is another feature from a different step, although it has more variance, but it still portrays a clear and generally monotonic trend. Now, by combining these features with other top features, you were able to train a health index model that can monitor the component's degradation over time. And this is the result of the solution after combining the top features and the appropriate machine learning technique, a health model dashboard. Now, as one can observe from the plot, the multivariate health has a clear and upward trend. And then a prediction algorithm is also used to estimate when the component will reach an acceptable level and when it should be replaced. The health model dashboard that you see here is implemented using our PDX platform, and we will explain this more with a demo towards the end of this presentation. For the remaining case studies on virtual metrology and chamber matching, they will be presented more as an overview. This way, we will have sufficient time for the solution demonstration, as well as some ample time to answer your questions. For those who are interested in learning more about virtual metrology and chamber matching, we would welcome the opportunity to discuss those examples in greater detail through follow-up meetings after the webinar. Our contact information will be shown towards the end of the presentation. Now, let's get into virtual metrology example. And with this, I hand it off to Aaron.
All right. Thank you, Edsel. I hope everybody can hear me correctly. So the key to the virtual metrology is to use the equipment center measurements to estimate the metrology measurement. Therefore, if you're able to do this, you can reduce the number of costly metrology measurements needed. With this particular solution, the idea was to learn the relationship between the sensors and the metrology data using machine learning regression models. Prior to developing the regression model, it's quite common to use similar pre-processing steps such as segmentation, feature extraction, and feature selection that were mentioned in the previous case study. If the model works well, again, the value comes from being able to reduce the number of those costly metrology measurements needed, saving both time and money. The general steps for the virtual metrology are again, pretty similar to the predictive maintenance solution, in such that we start with segmentation, feature extraction, and feature selection. However, the machine learning models used in this case are more focused on regression, which is more of an input to output relationship, as opposed to anomaly detection, which is looking at the deviation from normal. Not only this, but it also includes steps where we look to improve the regression models over time, such as model calibration and things like that. For this virtual metrology project, we worked with a major semiconductor OEM. A data-driven machine learning model was used, and we were able to achieve a very high accuracy for this application. After completing the solution, we were then able to refine the model template, such as looking at what features to extract, what regression models work best, and how to update the model correctly. This should allow us to quickly configure similar solutions for other customers in the future. In terms of the data set itself, there was 32 different signals collected that were considered for this application. For this case study, we looked at one key output measurement, which was the metrology figure. The sampling rate was around 1 Hertz for the data collection, and the project was approximately about 5 months long. As you can see from the graph here, the results from the PLS virtual metrology model worked quite well. Again, the green is what we would consider the actual values, and then the blue is the predicted. So you can see that over time, it closely matches those results. The residual plot, which again is the actual minus predicted, you can see here we had 2 thresholds. Again, this is plus or minus, I think about 1%. Which might have been 0.02. I'm not quite sure what it was exactly. But again, you can see that most of the points are within those acceptance criteria, with a few outside of that. The ones that did fall outside of this were mainly due to warm-up effects or temperature effects, and these are challenging problems to avoid. For the last case study, we will focus on a chamber matching solution created to improve yield. Variation in the semiconductor equipment chambers are typically present, and this variation can lead to quality issues and lower than desired yield rates. If you could adjust the chambers such that the behavior and sensor measurements are very similar or better matched, this would lead to better results and similar quality metrology outputs and result in better yield. From a solutions perspective, the key is to use various data-driven machine learning models to determine what parameters need to be adjusted in order to better match the chambers more closely. If this chamber matching solution can be accurately achieved, it would improve the product quality and yield. Again, chamber matching is probably one of the more challenging, or maybe even the most challenging of the 3 cases we've looked at today, since it involves several models working in tandem. The initial steps of segmentation, feature extraction, and feature selection are still there. So again, you're going through those first 3 or first 2 parts of the 6-quadrant chart. However, the baseline model can be used to showcase the differences in these chambers from the golden chamber and determine which variables are contributing to the difference amongst these chambers. So basically, you're trying to look at which inputs are causing the deviation and how do we adjust those. These inputs are then fed into a regression optimization routine, which relates the input settings to the feature values and determines what offsets in the features and thus inputs are needed to make the chamber behavior sensor values match more closely. We considered the regression optimization approach along with other approaches. In this example, we were working with an equipment OEM to co-develop this chamber matching solution. The solution finds departures from the baseline or golden chamber, identifies the contributing variables, and then relates that difference back to the chambers. And then we can use a regression model and optimization routine to determine what offsets are needed such that the chamber can be adjusted and then more closely match the golden chamber. Again, this was a very challenging project, but we actually have pretty good success with this in mind. Lastly, I'm going to walk through a quick demo here. So if I exit out of the presentation, so I think you guys can see my the dashboard here. So again, this would be what you would see in the main page here for your project. In this case, I think this project was for the predictive maintenance case study. Although there were, I think, 18 chambers, we decided to only include 3 equipments and a total of 10 chambers for this deployment. Just to make it a bit simpler. So what we're looking at here are 3 equipment, and within each equipment you can see how many chambers it has by these dots, and this is our grid view for the application. So if I click under equipment 1 here, you can see that 32% health is an aggregate of the 4 chambers it has here. And again, you can decide whether maybe that value is meaningful or not, but usually we want to look at the health of each chamber on its own. So if I click here, equipment 1B1, give it some time, and now this opens up the health page for that individual asset or chamber. You can see here the data comes from about October 2015 to March 2016, and it looks like we have about 2 PM cycles for this exhaustible part. You can see here over the first trend, it went from healthy to alert level, and again we have 3 colors here: green, yellow, and red. Green indicating healthy, yellow warning, and red faulty. The yellow is important because not only do we want to know when our machine is maybe needs to be taken down or we need to do something, but we also want to know that warning level at what time should I start taking a closer look at my machine. So that's why we can set these thresholds, and then emails or text alerts can be sent out to the maintenance technicians to say, hey, you need to go look at this asset at this particular time because it's past this threshold. In addition to seeing the overall health, we can also see what features are contributing most to it, and that's down here in this contribution plot. Now, the data has been cleansed for this, for IP concerns, but you can see that for this fault case, the first feature, or max step 9 P029, was the main indicator for that fault. So it allows someone, if they wanted to do a deeper dive, they could go in and say, okay, I want to look at this feature more specifically. In addition to also knowing where the health is at now, we also want to know, okay, when's it going to be in the future? And this is where we can use our prediction routine. If I hit show prediction, give it a second. Now it's able to make that prediction into the future and give us a better indication of when this asset is going to need maintenance. As you can see for this application, October to January, that was 3 months or so. You can see that this system is telling us we probably have another month and a half here. And with this information, now the maintenance technician can make decisions to decide, okay, let's say I have a PM cycle in April. Do I, just replace the part when the PM cycle goes, or do I wait and see, okay, can I get through another PM cycle with this asset? Lastly, instead of just looking at the health, we can look at the features themselves. And you can see that for this feature, we show a clear trend over time. Again, there's a shift during the maintenance event, but again, we were looking for features that look for change over time as opposed to their absolute values. If I plot the second feature here, again, we show a clear trend for both, PM cycles, but again, this one's a little bit more noisy, so maybe not the best indicator, but still one that was a good contributor to the overall health. And last, if I plot the last one here, again, this is the one that the model was picking out as the best indicator. And you can see that it does show a very clear trend over time in both PM cycles. So now, I think that's all I have for the demo. If I go back to the presentation, bring up the slide, and then I'll hand it back over to Edsel.
Thank you, Aaron. Now that you have seen the software and use case in action through the demo, we do want to highlight some general information regarding our PDX platform. Now, what you saw in the demo was the monitoring or visualization piece as a software. This is what the end user or the customer interacts with on a daily basis to get key health information in the form of a dashboard. But we also have reports, alerts, and notifications. Now, behind the scenes, the analyses or machine learning models are calculating the results either on a cloud or an on-premise server. Although not highlighted in this webinar, the PDX software does include its own data collection capabilities, targeted more for customers that do not have any data collection infrastructure in place or are looking to supplement additional sensors to their equipment. Maybe you are interested in adding a vibration sensor to monitor a turbo pump. But if you're interested to learn more about our data collection module, please refer to our website. We have had a webinar before highlighting that the data collection capability. So in summary, the PDX software includes many key functionalities for configuring and deploying these predictive solutions that we have just explained in the webinar. From connectivity to statistical or machine learning analytics, visualization, reports, as well as integration to other third-party enterprise applications, whether it's an MES, ERP, or CMMS. We do have APIs that allow us either to get information from others or be able to provide our results to your preferred visualization dashboard, for example. For implementing these solutions, one of the questions that we would likely ask would be, what data do you have or what data is already there? Now, if we can leverage existing historical data or MES data, this we believe is already a good starting point. And as needed, we can leverage on our PDX DIQ or data collection software to consider additional data either from external sensors or by tapping into the controller or PLCs. The models, the predictive models are configured and deployed using PDX software. And then additional integration is also possible depending on the customer use case, needs, and requirements. Although the framework illustrated here shows PDX on a cloud infrastructure, we are also cognizant and sensitive to other industries or organizations' concern and policies over data security. Hence, we are also open to on-premise installation of PDX as needed. With the background about some of our past work, as well as the relevant tools and software for configuring these solutions, you are likely wondering, how can you get started on this digital predictive initiative? So in this slide, we went ahead and summarized what would be needed for each of the use case discussed today. So for predictive maintenance, you would likely need the sensor data, as well as the maintenance records to configure and evaluate the predictive models. Now, specific to plasma etching equipment, it would also be great if you can have the optical emission spectroscopy or OS data handy. For virtual metrology, you would need not only the sensor data, but the quality or metrology data measurements as well. And finally, for chamber matching, the key additional requirement would be a way to test and validate the adjustments are working as expected. As you might have noticed while we were going through the different use cases, we typically follow this template or flowchart approach so that we can quickly configure and rapidly deploy our solutions. Machine learning is just one piece of this flowchart, but also critical to the process of developing predictive solutions include finding out what data you need to collect and incorporate into the model and what techniques to choose for pre-processing, feature engineering, and also the mechanism of deployment are all key pieces to this puzzle. So how do you work with us? We are quite flexible in working with our customers and partners, and We also understand the need to prove out the solution before it is eventually adopted and scaled. Our engagement framework includes an introductory or discovery process so that we may understand better your needs and pain points. This will be followed by a workshop to go in more depth discussion and eventually define the pilot project scope. The workshop will also provide the opportunity for the customer to learn more about PDX from the key functionalities, architecture, security, what have you. And then a proof of value that typically lasts 3 to 6 months to show you how the solution can work with a subset of machines. And with that, we will respond to the questions that were written down in the webinar question module. Feel free to ask your questions and we'll do our best to answer them. For the ones that we may not have time to get to, we will definitely reach out to you after the webinar with our responses. Here is one question. For the predictive maintenance use case, your case study focuses on extending components lifetime. Have you considered early detection of faults and reducing unplanned downtime for semiconductor manufacturing applications? So yes, you're right. We were able to, for the use case, the first use case described in this webinar, it was indeed for extending component lifetime. But we have had also work with our customers to work on temperature-related events, RF events, as well as endpoint events. Okay, the next question is more for Aaron. For virtual metrology, how do you judge the accuracy of the models, and what metrics should you consider in order to feel confident that the model could be used to replace the number of metrology measurements needed?
Yeah, so because virtual metrology, we're using regression-based models, or we're trying to kind of predict those measurements. Typically, it depends on the metrology variable you're looking at and how many. For our case study, since it was one, we were looking at more of what the percent or absolute error in the value and what was considered acceptable. And that's largely dependent on the customer. This should also be something to consider as with other statistical measures of accuracy, such as mean square error, mean absolute error, and etc. That answers your question.
Perfect, thank you. Oh, so one more question. So this one is more for implementation. How long does a typical semiconductor manufacturing project take? And can you give us a rough idea on the time duration? So probably I can answer first, and if Aaron has anything to add, please feel free to add your question, add your answer. So as noted in our presentation, our typical POC lasts from 3 to 6 months, but for semiconductor manufacturing, I think 3 months is a good estimate for the implementation, just because most of the time the data collection infrastructure is already in place. So we would likely need 1 month to set up to get the data for pre-configuring our models and fine-tuning it with the data that we received, and then another month probably to implement the solution in the customer, and then another month for either testing and letting the customer play with the system and then providing their feedback to us. Is that the right estimate, Aaron?
Yeah, I would agree with that. I mean, largely these kind of projects all depend on whether the data is available already. Assuming it is, the analysis can kind of take 1 month to 1.5 months for model refinement, and then the other deployment logistics. That seems like a reasonable timeline to me.
Okay, so one more question. So one of our attendees is asking, are the data models developed applied to each use case, or can they be generalized? Aaron.
Yeah, so there's kind of two aspects of generalization. So one is within a case study, can I, train a global model that works for all chambers? And largely, we would say that maybe depending on the application, usually it's a per chamber model. So for instance, you would have an individual model for each chamber, whether that's looking at, anomaly detection, where you're giving it a baseline that said, hey, this is a normal operation, and look at that difference. In terms of, application to application, like we said, for instance, with the virtual metrology, again, because we've, validated our results on, 3 or 4 or 5 different regression models, largely those pieces of the puzzle can be kind of taken from one application to the other. It's just that, from some case studies, you might have a different segmentation routine or a different, pre-processing technique. But usually once you reach that, the regression model and the optimization, those things are more, can work from one case to the other. So I think there's kind of two aspects of that, but I hope that answered your question.
Thank you. And with that, I think those are all the questions we have for today. We would like to thank everyone for attending today's webinar. We hope you found our presentation insightful, and please feel free to reach out to us if you have further questions or if you're interested to learn more about these predictive solutions discussed in the webinar. Have a great day and stay safe, everyone.
Thank you.